All right, so the problems that we really need to make sure we understand are the rate of work problems, because for the Math 3 EOC, these are the ones you are guaranteed to see. I see one on the EOC every year. Miss Rice, how do you see the EOC? Because I walk around and make sure you're not cheating, and as I walk around and make sure you're not cheating, I glance over your shoulder to see what the questions are. I'm intrigued, okay? I do not. Yeah, we can see them. Do I write them down? No, I'm not crazy, okay? I can see them. It's not cheating for me to see them. Yes?
I didn't know that math teachers were allowed to administrate math.
To what? Yeah. Back in the day, we couldn't, so math teachers can administer a math test if there are proctors. So if there's, another person in the room. And since we have proctors that, rove or whatever, that's what makes it so that we're able to. So, yeah. No, I can see, the types of questions that are on the test, and I was pretty aware that that was on the test anyway. It's on, the other thing is the rate of work questions are on the released form of the test, which is another reason I was aware that they were on the test. And it's also on the specs that are for, Math 3 anyway. So I was pretty aware that this was on there, but this seems to be the most common type of application question. It is the one you can count on being on the test. Does that make sense? Now, the nice thing, are you guys listening, is that these are pretty simple, and they actually use the solution method that we've already used, Wade, to solve for equations. So we just have to go through and solve them like we know how. So if we look at these questions, how did you guys feel about the first two examples? Did they make sense to you? They were okay? Now, this next one is a little bit more complicated because the variable is in a different spot. So let's read through the next question. It says, Marco can build a laptop twice as fast as Cliff. It just doesn't say what their times are. And then it says, working together, it takes them 5 hours. All right? So let's kind of walk through this. We've got Marco, we've got Cliff. I wrote Maro instead of Marco. Marco and Cliff. So we've got Marco that can build the laptop twice as fast as Cliff. So how do we write that with variables? Okay, so let's try this. Cliff would be 1 over x. 1 over 2x. Okay, let's think about this. If Cliff is 1 over, let's say 1 over 3, then Cliff is 3 hours. And then Marco would be 1 over 6. Is that what we want it to be? 1 over 3, 1 over 6? The other way around. Okay, so let's switch them. Okay. So whenever I have stuff like that with the variables, I always get them mixed up in my head about which one's supposed to be the 2x and which one's supposed to be the x. And what I just did with picking a number and plugging it in and making sure it makes sense, that is the strategy that I use to make sure that I've done the correct one for the correct person. So here, if Marco is 3 hours, then he'd have 1/3 of the job done each hour. And then for Cliff to be twice as long as him, so for Marco to be twice as fast, then Cliff would have to be 6 hours. That'd be the 2 times 3 for 6, for 1/6 of the job in an hour. Does that make sense? X and then 2x. All right, so let's go ahead and start writing it. So we would say 1 over x for Marco plus 1 over 2x for Cliff equals, and then what should it be equaling? Just 5? 5x? Think about the rest of them. 1 over 5. Because we always do all of these in terms of just how much could they get done in 1 hour? So if the whole thing would take 5 hours, then they could get 1/5 of it done in 1 hour. So remember we said 1/6 done in 1 hour, 1/4 done in 1 hour. Together it'd be 1 over x, because x would be the whole job. So they get 1 over x of it done per 1 hour. Does that make sense? So we're always thinking, how much could they get done in 1 hour? All right. So 1 over x in 1 hour plus 1 over 2x in 1 hour equals 1/5 of the job in 1 hour. All right. Okay, are we comfortable with that? Kind of. Okay, so now what do we do to solve? Sorry, I'm trying to zoom in. What do we do to solve this equation? Find the least common denominator, which is 10x. We need a 2, we need a 5, and we need an x. And so the least common denominator is 10x. So we have 1 over x times 10x. We have 1 over 2x times 10x. We have 1 over 5 times 10x. So if we're multiplying by 10x and dividing by x, what do we get? 10, okay. 10 times 1 is 10. Multiplying by 10x, dividing by 2x, 5, okay, the x's cancel. 10 divided by 2 is 5. 5 times 1 is 5. Multiplying by 10x, dividing by 5, 2x. So the x doesn't cancel, but 10 divided by 5 is 2. So we get 2x times 1 is 2x. Okay? So we get 15 equals 2x, and then what should we do? Divide by 2. And so x equals 15 divided by 2, which is 7.5. And so if Marco was 1 over 7.5, then how long would it have taken him to do the job by himself? 7.5 hours for Marco to do the job alone. Okay. Yes?
Why does that make sense? Because weren't we just finding for 1 hour? So wouldn't that equal only a fifth of the job?
So the 1 hour was 1 over x per hour. So it was 1 over 7.5 per hour. But it wasn't just x that was saying x per hour. It was 1 over x per hour. So since we're just solving for the x, we're not solving just the fraction. Does that make sense? So it's 1 over. So if we were to figure out what it is per hour, then per hour he can do 1 divided by 7.5. He's going to get that much of the job done for each individual hour. And then if you multiply that by 7.5, that's how you're going to get done in 7.5 hours. So that's 1 hour, and then that another 7.5 times, if he were working alone. Does that make sense? Kind of. So I'd say anytime you're getting confused, go back up to these sentences, kind of. So if it takes Fran 3 hours to do the job, then she can do 1/3 of the job in 1 hour, 1/4 of the job in 1 hour. So if they're working together, they can do 1 over x of the job in 1 hour. So we're kind of thinking of it as one person does a part, one person does a part, and so overall, if together they're each doing a part, then how much of that are they getting in one? Does that make sense? Okay. All right, let's go ahead and turn the page. I decided not to assign any of the inverse variation problems, mostly because that's something that you guys practiced last year a lot, and I don't expect you to be tested on it, and also it's something, because it's something you've done before, I wanted to focus more on something that you probably haven't done before. So I decided to give your other practice problems I wanted to give you guys the rate of work problems, but I decided for the other practice problems I would give you to do the current or the wind problems. So I don't really expect you guys to be tested on them as far as like the EOC goes, but I thought they were still pretty worthwhile because they are definitely true rational equation problems. So I wanted to do those. So this is turning to the very last page. That means that we are not going to finish these other two examples in the middle of the packet. You can put an X through them if you want. I am not going to look for those to be finished. And again, I made that choice because you guys had learned this material before. Did it feel familiar when we went over it? Inverse variation? No? Didn't, you were like, maybe, maybe not? No? Okay. All right, well, let's go ahead and look at the very last one. The very last page. So here it says a plane flies. So this one, I did copy paste when I did these, so it still says upstream and downstream, even though it's a plane question and talking about wind. So we're going to have to adjust how this works for this problem, because obviously it's not upstream and downstream if we're talking about wind. So if a plane flies 910 miles with the wind, so which one would with the wind count? Would that be upstream or would that be downstream? Downstream would mean that you're not having resistance. Does that make sense? With the wind means you're not experiencing the resistance. So let's cross out downstream and write with the wind. Go ahead and do that real quick. And then here, we're gonna be erasing part of this, but I'm just gonna write X plus W instead of C. So we have W for wind instead of C for current, just to make sure it makes sense. Okay. And then it can go 660 miles against the wind. So that's kind of like the idea of upstream, because when you swim upstream, you're swimming against the current. When you go against the wind, you're going against the wind. Okay. So we're going to write against wind right here. And so we're going to do very lightly X minus W, because part of that's going to get erased and replaced with a number. So the table's still going to work like the tables that we did for the current. It just is not going to say upstream or downstream. All right, so what number goes here? 660. Okay, what number goes here? 910. Okay. And then are we replacing the X or the W? The X. So they gave us, instead of telling us how fast the wind was, which would kind of be like telling us the speed of the current, instead of them telling us how fast the wind was, they told us the speed of the plane in still air. So the speed of the plane in still air is kind of like the speed of a boat in still water. So that means that the X is going to be replaced with a 305. So I'm going to go ahead and erase the X and put 305 there. Okay. So what should I write for time? So go back and look at if you look at your formulas. So distance divided by rate. So we're going to do 660. And honestly, it doesn't matter because you get the same answer anyway, but it's always nice to use your formulas and know you're doing it correctly. So 660 divided by 305 minus W. And then 910 divided by 305 plus W. And it says that the times that it can do these two things are the same. The plane flies 910 miles with the wind. At the same time, it can go 660 miles against the wind.
Wait,
Yes.
mine, the
Mhm.
top one, 660 over 305, is that plus or minus W?
This is minus W.
I thought you were both plus.
No, this is, sorry, I wrote it lightly. Okay, so we've got 660 over 305 minus W equals 910 over 305 plus W. Okay. And then how do we solve these? Cross multiply. And we got some big numbers. So what's 910 times 305? Okay, and then what do we get when we multiply these two? Okay, minus 910 W. And then what should we do? Okay, so I can add the 910 W. I can move this over. So when I subtract these, what do I get? Okay. And you end up getting a decimal answer, and that's okay. So if we write our decimal answer to 3 decimal places, what do we get? And what are the units? Miles per hour. So the wind is going approximately 48.567 miles per hour, which I think is really slow if we're talking about like wind speed.
No, it's
Wind speed when a plane is up in the air?
even down. How much money?
Like on the ground, no, but wind speed when a plane is flying, that's like. Wind speed should be way higher, shouldn't it? Yeah, but that's you're talking about on the ground. You're not talking about wind speed with a plane.
That's the worst possible thing on the ground. Just look this up.
Yeah, wind speed. Yeah, somebody look up typical wind speed for flying or something.
10,000 feet up.
We want to see how realistic our math problem is. I don't think it is either.
Did you make sense?
I did not.
Oh, okay.
I mean, I typed it up, but from another math teacher. I didn't like their font. It was too like kitschy. It was like Comic Sans or something. And I was like, I cannot give that paper out with self-respect.
With this in mind, horizontal winds, also known as cross winds, in excess of 30 to 35, about 34 to 40 miles per hour in general, prohibitive of takeoff and landing.
So for reference, average speed of this,
40 miles per hour.
Huh.
When they're done. Yeah.
Interesting. All right.
It's not unusual for an aircraft to travel through winds over 100 miles per hour, though.
what's good they don't usually become greater than 30 to 40 miles per hour.
Apparently, we're not pilots.
I mean, yeah, it's only
Turns
a
out.
job or whatever.
So it's your dream job?
Yeah.
Yeah. So if you're flying at like a normal flying speed, that's what I was thinking. Is that like on the ground? Yeah. Right. Well, 10,000 meters is 30,000 feet.
Yeah, that's like 30,000. And that was like over 100 miles per hour.
Yeah, that's like what I was thinking was like the higher in the air you go, the crazier the wind is. Okay. But like if you're flying this fast, we're not on the ground. This is not like when you were taking off and landing, because you're not going that fast. I still think we're right. Yeah, definitely we're right. Okay, next problem. A person swims 11 miles downriver, and the same time they can swim 7 miles upriver. The speed of the current is 4 miles per hour. Find the speed of the person in still water. So we're going back to the water problems. Upriver versus downriver, which I think upstream versus downstream. We could just leave those labels. Those are fine. So go ahead and fill out the table. I want you guys to fill out the table. I want you guys to come up with the equation that we're solving. So 11 miles downriver. At the same time, they can swim 7 miles upriver. The speed of the current is 4 miles per hour. Did you do your problem already?
Someone puts my pen as a name.
What the?
Well, that sounds like personal problem.
I just want to wash my hands.
I just want you to do your math. Oh, there. That's easy. It shuts off. Yeah. Is it, so if you got a crazy ring, if it is is because you mixed up still water versus current rate. Did you plug something in for the x or the c? Minus 4x plus 4? Okay, so this is... Oh, like the person was swimming very fast.
Yeah.
Yeah. That...
Like, am I right thinking that? But that's really crazy.
I got a fast speed also.
I thought, okay.
Jack is like, I'm a swimmer, and never in my wildest dreams could I swim this fast.
Okay.
Is that true, Jack? I am not a swimmer, and so I solved this problem, and I didn't even think about it.
I didn't think about it because I was sitting there. I was looking out, like, that's kind of crazy. But, wow.
I swim that fast across my bathtub. I mean, my bathtub is very small, so I can go as fast as I want. Get to the other side, done. Fast.
Why are they faster in still water than going down?
Wait, do you play hockey? For real?
Yeah, this problem doesn't really make sense, does it?
Play hockey? What team are y'all on? Are y'all like local?
So we found that this problem doesn't really make sense. I think we've mathematically solved it, but it doesn't make sense in real life, is what we're finding. Okay. So what have you guys come up with? This is the equation I got. Is that what you guys got? Okay. And then this is what I was cross multiplying. This is what I got when I cross multiplied. Yep. And then this is what I got next. Okay. And then oh shoot. And then nobody saw it. Did anybody see the spoiler? No? It's good? Nobody's paying attention, so nobody saw. Okay. And then I got this. And then we got this, and we said there's a few things wrong with this. Number one, that person is swimming awfully fast. And then they were swimming faster in still water than they were with the current helping them, which was strange, because that's not really how it works. But okay. That's like, I don't know, I run faster on asphalt than I do on a treadmill with it helping me.
Also, actually, asphalt you get better grip, right? When you're running, you feel like you're like,
What's for your life?
They're using what energy?
I don't know. Or like I was biking faster by myself than I was when I was biking with the group and I caught the drift or whatever when I was drifting. Is that the right word? Drifting? When you like catch the speed of the group? Does that happen with cross country too? When you like are running with a group of people, you don't. That doesn't happen. Oh, okay. No, it truly does work with bikes though, because I used to when I lived in Portland, Oregon is a very bikeable city, and there was this little hill right before my house, and I hated biking up this little hill, and then once I was behind a group of bikers, and I got real close to them, and I totally just coasted. I just, like, they pulled me along, and I was like, this is the best! I didn't have to ramp the hill today! Yeah, it's great. Yeah, it totally, like, I went up that hill like I was doing nothing. Legit. Until you've done it yourself, you do not know how much of a difference that makes. Whew. Yeah. All right.